In this video tutorial, we are going to see about the solubility of drugs. Solubility phenomena. So what in solubility phenomena, we should know what is solution, what is solubility, what is saturated solution. So introduction to solubility phenomena. Solution is a system in which the molecule of the solute are dissolved in a solvent. Solubility may be defined as a concentration of solute in a saturated solution at certain temperature. So it is the intrinsic property of the solute. Next comes the saturated solution. Saturated solution is the one in which the solute in a solution is in equilibrium with solid phase. So how does the solute and the solvent is getting interacted? We can call it as like dissolves like. So polar substances which tend to dissolve in the polar solvents, while the nonpolar substances tend to dissolve in the nonpolar solvents. The more similar the intermolecular interactions are, the more likely one substance is to be soluble in the another. So types of solvents: polar solvents, non-polar solvents, and semi-polar solvents. So, what are the factors which is affecting the solubility? So, the solubility of the substance mainly depends upon the polarity, dielectric constant, association, solvation, internal pressures, acid-base reactions, chemical, electrical, and structural effects that leads to mutual interaction between solute and solvent. So in solute and solvent interaction, now we are going to see about the polar solvents. So polar solvents which dissolve ionic solutes and polar substances. The solubility of the drug in polar solvent depend upon the polarity of the solute and the solvent, the ability of the solute to form the hydrogen bonds. Water dissolves phenol, alcohol, aldehydes, ketones, amines, and other oxygen and nitrogen containing compounds that can form hydrogen bonds with water. So third point is the ratio of the polar to non-polar groups of the molecule when additional polar groups are present in the molecule like propylene glycol, glycerin and the tartaric acid. Water solubility increases greatly. So as the length of the non-polar chain of an aliphatic alcohol increases, the solubility in water decreases. So the straight chain monohydroxy alcohols, aldehydes, acids with a more than 4 carbons cannot enter into the hydrogen bonded structure of water. Hence they are less slightly soluble. So and then the branching of the carbon chain, which reduces the non-polar effect and leads to increased water solubility. So example, tertiary butyl alcohol, which is miscible in all proportions with water, whereas the N-butyl alcohol dissolves only to the small extents. And next one, the non-polar solvents. Second type, ionic and the polar solutes, which are not soluble or only slightly soluble polar solvent, non-polar solvents. Example, hydrocarbons. So, because non-polar solvents are unable to reduce the attraction between the ions of strong and the weak electrolytes because of the solvent's low dielectric constants. And these nonpolar solvents cannot break covalent bonds and ionize weak electrolytes because they are aprotic. Aprotic means no hydrogen bondings. Nonpolar solvents cannot form hydrogen bridges with non-electrolytes. So nonpolar solvents dissolve nonpolar solutes with similar attractive forces through induced dipole interaction. That is London forces. Example, carbon tetrachloride can dissolve oils and fats. Next comes the semipolar solvents. Semipolar solvents can induce certain degree of polarity in non-polar solvents. So semipolar solvents act as an intermediate solvent that generate miscibility between polar and non-polar liquids. Example, acetone increases the solubility of ether in water. Next comes the difference between the ideal and the real solution. So ideal solution is the one in which there is no attraction between solute and the solvent molecules. So ideal solution is the one in which there is no change in properties of the components than that of dilutions. So this ideal solution will be obeying the Raoult's law. Next, the real solution. In real solution, the cohesive forces of attraction between A and A exceeds the adhesive force of attraction existing between the A and B. So alternatively, the attractive forces between A and B may be greater than those between the A and A or B to B. This may occur even through the liquid forms solution in all proportions. Such mixtures are real or non-ideal, and this real solution they do not obey Raoult's law. So, what is Raoult's law? In ideal solution, partial vapor pressure of the each volatile constituents is equal to the vapor pressure of the pure constituent multiplied by its mole fraction in the solution. So, two constituents A and B is taken, in which the PA and PB are the partial vapor pressure of the constituents, and XA and XB are the mole fraction of concentrations. So vapor pressure composition curve for an ideal solution is shown here as a binary mixture, binary in two mixtures. Deviation from the Raoult's law. So this can be explained by the Henry's law also. There are two types of deviations, negative deviation and the positive deviations. Negative deviation from the Raoult's law. Negative deviation in the sense when the adhesive attractions between molecules of the different species exceed the cohesive attractions between like molecules, the vapor pressure of the solution is less than that expected from Raoult's ideal solution law. And this is called as a negative deviation occurs. Example, chloroform plus acetone. The vapor pressure composition relationship of the solute cannot be expressed by the Raoult's law, but instead we can explain through the equation Henry's law. So Henry's law applies to the solute and the Raoult's law applies to the solvent in the dilute solution of the real liquid phase. Next comes the positive deviation from the Raoult's law. So when the interaction between A and B molecule is less than that of between molecule of the pure constituents A to A or the A to B, the presence of B molecules reduces the interaction of A to A molecule correspondingly reduce the B to B interactions. So accordingly, the dissimilarity of the polarities or internal pressure of the constituents results in a greater escaping tendency of both A and B molecules. So the partial vapor pressure of the constituents is greater than that expected from the Raoult's law, and the system is said to be the positive deviation. Example, benzene and ethyl alcohol. Next comes azeotropic binary mixture. In this mixture of liquid that has a constant boiling point because the vapor has the same composition as the liquid mixture. So the boiling point of the azeotropic mixture may be higher or the lower than that of any of its components. So the components of the solution cannot be separated by the simple distillation method. So solubility of the liquid in liquid. So two or more liquids are mixed together in the preparation of pharmaceutical products. Example, aromatic water, spirit, elixir, lotion, sprays, or medicated oils. This system can be divided into two categories. One is completely miscibility and the second one is a partial miscibility. Complete miscibility means polar and the semipolar solvents such as water and alcohol or alcohol and acetone are said to be completely miscible because they mix in all proportions. So nonpolar solvents such as benzene and carbon tetrachloride are also completely miscible. So these liquids are miscible because the broken attractive forces in both pure liquids are re-established in the mixture. Next comes the partial miscibility. When water and phenol are mixed, two liquid layers are formed, each containing some of the other liquids in the dissolved state. It is possible to calculate the composition of each components in the liquid conjugate phases and the relative amount of each phase from the tie lines that cut the binodal curve. So this is the phenol water system phase diagram. Next comes the in partial miscibility. Liquids are influenced by the temperature. So the two conjugate phases change the homogeneous single phase at the critical solution temperature, which is otherwise called as consolute temperature. Example, trimethylamine and water, which exhibits lower consolate temperature, below which the two membranes are soluble in all proportion and above which two separate layers are formed. So example nicotine and water, which shows the both upper and the lower consolate temperature with an intermediate temperature region in which the two liquids are only partially miscible. So final type in A type exhibits which exhibits no critical solution temperature. Ethyl, ether and water shows partial miscibility over the entire temperature range at which the mixtures exhibits. So this is the two system, solid and the liquid phases, where which is called as a eutectic mixture, where the salal and thymol solutions, which is turning into the eutectic mixture. So increasing the percentage of thymol in the mixture till reaching the 100 percentage. So this phase system, salal thymol system shows the single liquid phase system, a region containing solid salal and conjugate liquid phase, and the region in which the solid thymol is in the equilibrium with the conjugate liquid phase, and the region in which both components are present as a pure solid phases. So at 25 degrees Celsius, the conjugate liquid phase consists of 53% thymol and solid phase 100% solid thymol. And at 15 degrees Celsius, conjugate liquid phase consists of 37% thymol and solid phase of the 100% solid thymol. So below 13 degrees Celsius, two solid phases, thymol and salal, will be forming. So lowest temperature at which the liquid phase can exist in system in is 30 degrees Celsius, which is a mixture containing 34% of thymol in salar. So this is called as a eutectic point. So this is the three component system, ternary diagram, phase diagram. This is the ternary phase diagram of having water, oil and surfactants. So solubility of a gas in a liquid. So the solubility of gases in liquid depends on the mass of the gas molecules, pressure, temperature, presence of salt, chemical reaction with solvent. So the first one, the mass of the gas molecules. The solubility of gas molecules typically increases with increasing mass of the gas molecules. So the largest the mass of the gas molecules, the stronger London and the Debye forces is between gas and the solvent molecules. Next comes the pressure. So gases increase in solubility with an increase in pressure. Increasing the pressure results in more collisions of the gas molecules with the surface of the solvent. So more solvations, hence greater the solubility. So this can be explained through the Henry's law. So the effect of the pressure on the solubility of the gas is expressed by the Henry's law. So Henry's law states in a very dilute solution at constant temperature, the concentration of dissolved gas is proportional to the partial pressure of the gas above the solution at equilibrium. So the partial pressure of the gas is obtained by subtracting the vapor pressure of the solvent from the total pressure above the solution. If C2 is the concentration of the dissolved gas in the grams per liter of the solvent and P is the partial pressure in milliliter of the undissolved gas above the solution. So Henry's relationship may be written as C2 is equal to sigma P. So sigma is equal to 1 by K, which is the solubility coefficient. Next comes the temperature. So gases decreases in solubility with an increase in temperature. So increasing temperature causes an increase in kinetic energy of gas molecule, which leads to breakdown of the intermolecular bonds and gas escaping from solutions. Example, carbon dioxide gases escape faster from carbonated drink as the temperature increases. Next comes the presence of salt. So dissolved gases are often liberated from the solution by the introduction of an electrolytes, example NaCl, sodium chloride, and sometimes by a non-electrolytes, example sucrose. This phenomena is known as the salting out process. Next, pH. So system of solid in liquid include the most frequent and important type of pharmaceutical solutions. Most drugs belongs to the class of weak acids and bases. They react with strong acids or bases to form water soluble salts. So acidic drugs are more soluble in solution. Example for acidic drug NSAIDs, non-steroidal anti-inflammatory drugs, where the ionized form is the predominant one. So in basic drugs, example anatidine, are more soluble in the acidic solutions, where the ionized form of the drug is predominant. So carboxylic acid containing more than 5 carbons are relatively insoluble in water. However, they react with dilute NaOH, carbonates and bicarbonates to form soluble salts. So the fatty acids form soluble soaps with an alkali metals and insoluble soaps with other metal ions. So phenol is a weakly acidic and only slightly soluble in water, but is quite soluble in dilute sodium hydroxide. So this is a drug as a weak electrolyte and dissociation. So PHP is equal to pKa plus log S minus SO divided by SO. So where PHP is the pH below which the drug separates, S is the total solubility of the drug dissociated plus undissociated. SO is equal to molar solubility of undissociated form of drug. So substrates can influence the solubility by affecting the solute molecular cohesion and its interaction with the water molecules. So polar groups such as OH capable of hydrogen bonding having high solubility. So hydroxylic acids such as tartaric citric acid are quite soluble in water because they are solvated through their hydroxyl groups. So non-polar groups such as CH3 and Cl are hydrophobic having the low solubility. So the position of the substance on the molecule can affect the solute molecular cohesion and its interaction with water molecules and hence its solubility. So example, OH group of salicylic acid cannot contribute to the solubility because it is involved in the intramolecular hydrogen bondings. So the substitution in ortho, meta, and para shows the symmetric particles can be less soluble than the asymmetric ones because they form a compact crystals which require more work to separate the particles, while the asymmetric particles pack less effectively in crystals. So Sol- so next comes the solvent. Frequently, the solute is more soluble in the mixture of the solvent than in the single solvent. So the solvent which is in combination with the main solvent increases solubility is known as the co-solvent. Next comes the crystal characteristics. So different crystal forms of the same substance is known as the polymorphs, which possess different lattice energies. The polymorphic form with the lowest free energy will be the most stable one. So the less stable forms with the highest energy will be the most soluble one. They tend to transform into the most stable form over time. So the solubility of the crystalline material and its rate of dissolution can be increased by using the metastable polymorph. Many drugs which exhibit polymorphism, example steroids, barbitrates, and sulfonamides. So incorporation of the solvent molecules into the lattice structure of crystalline material during crystallization will result in solids that are called as solvates. If water is a solvating molecule, the solids are called as the hydrates. The interaction between substance and water that occurs in this crystal phase reduces the amount of energy liberated when the solid interact with the solvent. So water. So therefore, unsolvated crystals will dissolve faster. Next comes the complexation. So this complexation can increase or decrease the solubility of the drug depending whether the formed complex is water soluble or insoluble. Example, cyclodextrin can form a water soluble complexes with most drugs thus increasing their water solubility. So tetracycline can form water insoluble complexes with various metal cations. Therefore, tetracycline solubility is decreased in the presence of those metals. Boiling and melting point. In general, aqueous solubility decreases with increasing boiling and melting point. This is because the higher the boiling point of the liquid and melting point of solids, the stronger the interaction between the molecule in the pure liquid or in the solid state. Next comes the particle size. So, particle size, the solubility increases with the decreasing particle size due to the increased particle surface area, meaning more of the solid is in contact with the solvent. These are the solubility phenomena. Now we are going to see about the distribution phenomena. So, this under distribution phenomena can be explained by the partition coefficient K. So, if the liquid or solid substances is added to the mixture of two immiscible liquids, it will become distributed between the two layers in a definite concentration ratio. So, if concentration 1 and concentration 2 are the equilibrium concentration, of the substance in solvent 1 and solvent 2, the equilibrium expression becomes C1 by C2 is equal to K. So the K is the equilibrium constant, which is known as the distribution ratio, distribution coefficient, or the partition coefficient. So partition coefficient can be explained with the example when the boric acid is distributed between the water and the amyl alcohol at 25 degrees Celsius, the concentration in water is found to be 0.0510 mole per liter, and in amyl alcohol it is found to be 0.0155 mole per liter. So, what will be the distribution coefficient? So, when we are simplifying it, we can get 3.29. So, no convention has been established with regard to whether the concentration in the water phase or that in the organic phase should be placed in the numerator. So therefore it can be expressed as the 0.304. So one should be always specify which of these two ways the distribution constant is being expressed. So partition coefficient is a parameter that characterizes the compound in its unionized form for water and an immersible model lipid solvent, octanol. So octanol was chosen as a model lipid phase because in it most closely simulates the properties of biological membranes. So determination of P or log P values involves the placing of the drug compound along with the two immiscible solvents in the separating funnel. So molecules of the solute will distribute in each phase until equilibrium is established. So the ratio of the two concentration is the partition coefficient or distribution coefficient. So the interpretation can imply that the drug has a affinity for the water and the oil membrane layer. Therefore, there is a equal distribution between the water and the oil layer. Drug has affinity for the water or hydrophilic layer. So the partition coefficient uh, substitutes that increase the p-value by aryl alkyl halogen groups. They substitute that decrease the p-value of carboxylic groups NH2O, CO, and OH groups. The applications of partition coefficient in pharmaceuticals. So we are having various applications in the current pharmaceutical interest. The number one, the preservation in oil water system. Number two, the absorption and distribution drug throughout the body. Number three, the extraction of active ingredient from the crude drugs. Next comes the apparent partition coefficient. So when the association dissociation of the drug occurs, the situation becomes more complicated. Example, benzoic acid associated in the oil phase and dissociates in the aqueous phase. So drugs that are weak acids or weak bases ionize in water depending on their pKa and on the pH of the aqueous phase. So in general, ionized structure cannot partition in octanol or other hydrophobic solvents. So p-value cannot be used to assess the true distribution of the ionizable drug. in the two immiscible phases, simply because its value is dependent on the ionic state of the drug, which in turn depends upon the pH. So this is the distribution apparent partition coefficient of octanol and water. So reference for this solubility of the drug has been taken from the Martin Physical Pharmacy, who is by authored by Lippincott Williams and Wilkins. Thank you.